Okay. So first of all, I wish you all a very happy and healthy 2023, excuse me. And today, this is my pleasure to introduce the first two speakers of 2023. So we start with Guido Mulla, who's a physics researcher at the University degli Studi di Cagliari in Italy. And Guido is a highly recognized expert in hybrid structures based on porous silicon, with a high focus on pore filling processes, and is doing this research for various applications, including biosensing and photovoltaics. And today, Guido will be talking about pore filling in porous silicon, a complex task with unexpected advantages. Guido, please.
Thank you for the introduction. Let me share the screen. And how this. Sorry, my computer blocked Zoom. Just 1 second. Sorry, it tells me that I have to leave the meeting for 1 second just to allow it to share the screen. Just 1 moment. I should work. Can you see my? Okay.
Yes, it does. Thank you, Guido.
Sorry for the inconvenience. So let me first thank the organizer for this invitation, and it's a pleasure for me to talk to you about pore filling, which is in porous silicon, and which is a very complex task. We know that porous materials have interesting properties. They have developed inner volume. They have allowed to develop a surface, and they offer, thanks to these properties, the possibility to build new hybrid materials where you insert something in the pores. However, the filling of the pores can be extremely challenging task, because when you go to tiny pores, say below 80 nanometers in diameter, then you start to have several issues becoming from the fact that the pores are not regularly shaped, and that the connection between your material and the pore structure can be complex. I will show you two examples of this. The first is the use of erbium in porous silicon, where the use of a wide range of characterization tools will be necessary to understand what happens. And this will lead to a new paradigm, a new way of looking to this erbium doping to achieve a light emitting device. And then I will describe you the results on melanin on porous silicon to improve the light absorption, and how the use of a computational experimental approach will allow porous silicon to behave not only as a matrix for hosting the polymer, but also as a sensor itself to probe the properties of the polymer. So let's start with the erbium in silicon. The main problem is that porous silicon has not the porous silicon, erbium has a clustering attitude. So when you try to increase the erbium content to have infrared emission, light emission, you will have in return erbium clustering that will hinder the light emission. So the use of porous silicon will allow to have the larger developer surface as a place where to distribute correctly the erbium, and the flexibility of the electrochemical impregnation process that will allow also to some flexibility in addition to the surface. So to achieve the result, you need to fully understand how the electrochemical process goes on, and you need to use a multidisciplinary approach to understand and solve this dilemma between erbium clustering and erbium content for the optimum result. The first thing you notice is that when you do constant current doping on porous silicon with erbium, you have the current density that becomes a pivotal doping parameter by itself. So that if you measure the current density as related to the inner surface of the pores, then you notice that for low current densities, you have a single process, which is described here by the behavior or the voltage versus the transfer charge in green. You have a single process, single transient, which is what you expect for a normal deposition by an electrochemical process. However, if you go to higher current densities, then your system changes, and you have this double transit here that will be also followed by a third later on, that I will describe to you later. And this demonstrates that your process has changed. From a single process, you have multiple processes, the chemistry is changing. And in particular, we show that these first transients indicate the transition from a normal solution to a denser solution, where the formation of erbium methanolate led to a stable and reliable doping, while for lower current density, you are putting erbium, but this erbium is not fixed on the surface. When you wash up your system, you will directly go away. So to understand how erbium is distributed on the surface, we relate it to electron tomography. And here we can see the white part, which are erbium, and the gray part, which is the silicon structure. And you see that there is a gradient, which is typical, unfortunately, on tiny pores. But the interesting fact is that here, where you have a lower erbium content, you observe clustering at any depth, so at any erbium concentration. So if erbium forms clusters at any doping level, this means that even if you try to find the better compromise between the content and the light emission, you will still have this clustering problem. So you can go to other regions where you have higher erbium content and try to understand how the doping behaves. And you notice that erbium nanoparticle coalesce and form a covering of the walls, while not clogging the pores, which is an important parameter why you want to understand how to fill at best your pores. If you look here, then you are interested in luminescent properties. And here is a result for the photoluminescence emission varying the doping level. Take into account that the normal doping level are 1–2%. This is what is being used in silicon-rich oxide structures as an optimal level between the content and the light emission. And above, you see that above this level, which gives very low photoluminescence emission, you have a sharp and intense peak that lowers again when you start to increase the erbium content again. If you look at the time resolved photoluminescence, you can see that where you have the highest luminescence peak, you have two different time constants that are indicating that you have two different erbium compounds present in your structure. While when you go to higher content again, you have again a single transient. So this means that this particular condition, when you have the highest peak, you have also the presence of two different compounds that can be identified as silicon, erbium silicate toward the silicon interface, and erbium oxide in the inner part and on the surface of the sample. A further check can be done to understand if this luminescence is regularly distributed along the sample. So this is a stop measure of specially resolved photoluminescence, where you can see that the emission intensity is regularly distributed toward the surface, not completely homogeneous, but this is normal also because when you fill tiny pores, it happens. It has been observed also with nickel filling. Sometimes some pore is empty or almost fully empty for just the chemical distribution of the material on the surface. But on the whole, you have an homogeneous distribution. So what happened when you combine all this information together? You can see here the full extension of the applied voltage versus erbium content behavior, where you have the first two transients I described you before, and the third transient, which is much slower than the two first. And at the photoluminescence, the intensity as this bar, colored bar. In the first part, you have the erbium gel formation where the solution densifies and you start to deposit some nanoparticle on the walls that later on becomes a full coverage. And then you start to have your emission intensity raise significantly just when you start to really fill your pores with the thickening of the pore wall or the coverage of the pore wall. And you have your maximum when you have the pore completely filled with the two components. In the clear here is the erbium oxide, and this is the erbium silicate, which is a tiny layer covering the porous surface. When you increase and you have your erbium oxide on top, then your luminescence decreases. And this shows that your optimum is when you have the two compounds present, so the silicate and the oxide. What is interesting here is that in this region, when your previous maximum was indicated, so 1–2%, you do not have a significant luminescence. But if you go to this situation when you have the pores which are filled and just a tiny covering layer of erbium oxide, at this moment you have the optimal intensity. So you have to change your paradigm. Instead of looking for a compromise between the loss of luminescence given by the clustering of erbium and the gain you achieve by increasing the amount of erbium, you have to look for a completely different system where you fully fill your pores. You forget about clustering because you're really filling up your pores. And the heating up, you have a matrix, which is silicon, which can be used whatever you want for electronics, and a light emission, which is stable, reliable, and intense. So the understanding of the filling process leads you to a change of paradigm for your layer, for your device, which is not possible just trying to fill the pores and seeing how is the best compromise between low content of erbium. So this is the first example I wanted to show you. The second one is the case of melanin in porous silicon. Silicon and porous silicon have low absorption in the visible range, and while they are used for photovoltaic panels, in any case, they still have the need to be thick because otherwise the absorption would be inefficient. Many strategies have been tried to optimize the system, in particular trying to modify the surface of silicon by patterning the surface or using porous silicon as an anti-reflecting layer. But we can do something better, which is we can use polymer, which are P-type mainly, in particular melanin, which is also a highly absorbing polymer, to put inside the a porous silicon structure made with N-type silicon. So you will have a bulk heterojunction, that is a large active area made by the PN junction between the polymer and the type silicon. And you have to understand how this melanin behaves within these small volumes to control your system. First question is the system working? Of course, the answer is yes. Here is comparison of what happened with the normalized photocurrent obtained measuring the photocurrent with low pass spectra filters, so that your spectra is expected to increase as long as you go from larger to a smaller wavelength. Because if you have absorption, the range which is considered is those towards the longer wavelength, so your overall photocurrent must increase if you have absorption. If you compare this has been obtained on empty porous silicon with impregnated porous silicon, then you see that your absorption increases much quicker than what happens on empty porous silicon. And so that it is proof that your absorption rate has been improved with respect to empty silicon. And if you compare the absolute values, you can see that with impregnated porous silicon, you can have photocurrents which are even 2 orders of magnitude higher than what you can have on empty porous silicon. So the system works, but it has some drawbacks. First is that the device lifetime is just a few days. You lose the humidity level dependence, which is typical of melanin conductivity, which increases with increasing humidity level. And you do not have real control over your system by modifying the inner porous silicon surface or modifying the impregnation or the polymerization process. And this is important because it proves that the only way to understand what happens to your system is to understand what happened to the polymer. But this is a problem in the sense that the polymer at the nanoscale are very difficult to characterize. So we try to understand the system by making some calculation, and we learn that the melanin, when it makes an interface with silicon, tends to densify, and this denser region is not very thin because it goes up to about 5 nanometers. So what are the implications of this densification is also that the mobility of water molecules, I told you about the sensitivity the melanin should have to water. So the water mobility within the system is really reduced when you go to denser polymer, while it's normal when you go to the bulk-like polymer. But if you go to tiny pores, which is the kind of pore we use initially, you can see that 5 nanometer of a 20 nanometer pore means that you have most of your volume occupied by the denser polymer. While if you would like to look at larger pore, then your volume will be mostly occupied by a bulk-like polymer. What are the implications? If you think about tiny pores and you take into account also that the polymerization process produces hydrogen peroxide, which is a strong oxidant for the silicon surface, you see that you start your polymerization, the hydrogen peroxide cannot go in the inner part of the pore because it's occupied by a dense polymer, so it cannot move, and it goes towards the interface, where the side effect is the oxidation of the surface, and therefore the production of an insulating interface that will stop the working of your system. For large pore, instead, you expect a different behavior, because when you start your polymerization process, then you are still having the denser polymer, but it will just be on the sides of your pore. And the hydrogen peroxide, you have the possibility to move inside the pore, where the polymer is large, and the water molecule or hydrogen peroxide can move freely, not freely, but more easily. And at the end, the hydrogen peroxide can be expelled from the surface. So with this model, which implies understanding of what the polymer does at the nanoscale, we make some tests. So this is what happened with tiny pores. We are looking at the photocurrent intensity over time, and you can see that after a couple of days, it goes to 0 with tiny pores. When you go to a larger pore, then the difference is quite remarkable, since you have significantly high photocurrent, and you may still have measurable photocurrent after about 2 months. This means that since you have a stable system, you can also try to optimize better your system. And in particular, you can work on the stability of the system with respect to initial condition, the polymerization process, etc. This is just an example of what happens. Is that this is a sample that has been left on the shelf without any control for some months during the lockdown during COVID, and you can see that even without any kind of control, at the end of the period, the sample is still extremely sensitive to the water content, and you still have the high peak due to the increase of the photoconductivity at high water level. Then we can see our porous silicon structure as a sensor. We can ask ourselves a question like, can we compare different melanins, so different monomers that lead to differently organized polymers in the pores? Yes, this is a sensor for water, where we compare the DHI versus DHN. There are two monomers. This is the dihydroxyindole, this is dihydroxynaphthalene. I won't go into the chemical details of this, but the point is that the behavior of these two melanin are completely different. And while your system is still stable, with DHI, you have an unreliable connection while when you use DHN, which is more ordered structure, you have a reliable system, not perfect, but still very good sensitivity to water. So you can think about building a water sensitive device, or better still, using your porous silicon to sense nanoscale properties of polymers. Nanoscale properties are really difficult to measure, and in our case, where you go from 10 nanometers, 15 nanometers to 60 nanometer diameter, in reality, you are looking to a thickness which is related to the radius and not to diameter. So you're looking to 5 to 30 nanometer thickness of your polymer. So to conclude, a detailed understanding of the filling process in tiny pores, where I mean something below 80 nanometer in diameter, is needed to understand and be able to control in detail the filling process and to optimize the materials and the device you want to fabricate. Pure silicon can be used then as a tool, not only as a matrix, but also as a tool to probe the nanoscale properties of melanins or polymers in general. And this is really a new aspect of this material that gives access to something that is really not observable experimentally otherwise. And so I hope to have convinced you that filling is a complex task. And when you go to these tiny pores, you have a lot of problems, issues, and aspects to consider, both for organic and inorganic materials. Thank you for your attention.
Thank you very much, Guido, for this great presentation and presentation of the difficulties and advantages. It's very interesting to also always to deep into pores and see what's going on. It is time for question. We have a few time for that.
Good morning, Frederic. I have a question. This is Luis.
Hi,
Hi, Guido. Nice presentation. I just have a curiosity. You infiltrate in the pores melanin as organic material, right? So my question is if you have to try to infiltrate other organic materials, organic materials used in, for example, electronics, so like pH3 and other materials used in organic electronics, and see if there is any difference or different performance in your system.
We tried several polymers, but in particular we tried with polyaniline, and we are starting to pH3 and P dot, etc. We didn't have a really large set of measurements at the moment, but for polyaniline, for instance, we noticed that the difference is remarkable, and because polyaniline is another polymer that has sensitivity in this case to acidic or basic environments. And in tiny pores, you lose this sensitivity, while in larger pores, you gain again this property. So the effect of the interface is really hard to for the polymer properties. And we tried this with chemical infiltration and with electrochemical infiltration. We tried to modify the surface by attaching some molecule to the surface to have really covalent bonding between the polymer and the surface. And while the covalent bonding can help because it will change the way the polymer feels the silicon surface, still the change of the size can have other effects on the overall properties, on how this is sensitive, how it is reliable. Also because the tiny pores tend to be irregular and the larger pore have to be more regular. I didn't mention, I just mentioned here, but we use also the process we patented that is called electrochemical nanolithography that allows to have a better distribution of pores. And this means also a better size homogeneity of the pores. So when you make your study on tiny pores, you usually have all kinds of sizes, so small, but still with a large variation. When you have this process, then you have all pores with the same size and distribution. You can control the distribution and the ordering of the pores.
Okay, thank you. Thank you. Very interesting. Thank you very much.
Thank you.
Thank you, Guido. Any other question? I may have a quick one, Guido. So you said that you impregnate the pores. In this case, with melanin, it's with the precursor, and then you process the polymerization is in situ.
Yeah.
And you probably did it, and it's something that you just mentioned. Have you tried to impregnate directly with the polymer so that you can eventually get a homogeneous distribution of the density of your polymer?
The problem with the melanin is that it makes a huge polymer, so you cannot really infiltrate the full polymer inside the material.
Okay.
Other polymers are shorter chain, so you can try. We try with some organic polymer, and we show that it is possible to put them inside. But with melanin, it's really hard because it makes irregular chains, and it can polymerize. It's a flat molecule by pi stacking or lateral stacking, and this is completely irregular. So you can really try with the polymer itself. But the polymerization process can be changed because it can make just with ammonia, or you can try hydrogen peroxide and several processes to oxidize, which is the process to obtain the polymerization.
Okay, thank you.
You're welcome.
Other question, please, for Guido on this very interesting process. So if not, then we can move on to the next talk of this webinar session today. And the second speaker today is from Top University of Ankara. She is Itir Koyman. We are very happy to have you, Itir, presenting your work today. Itir is currently an assistant professor with the Department of Electrical and Electronics Engineering in Top University, and she's also a researcher at TÜBİTAK UMA in Turkey. So it seems that Itir has at least a double activity. She's very busy, and she's interested in nonlinear devices, micron-sized and nano-sized, and inspired, like you said, inspired by biology. So please, Itir.
Thank you for the kind introduction, and thank you for having me. Let me share my screen. Okay.
Works.
I don't think I switched. Oh, okay. It's in presentation mode, yeah?
Yep.
Yeah, okay. Right. So as Frederick kindly introduced me, I'm from a slightly different background to most of you, I assume. I'm an electrical and electronics engineer, And today I'll be talking about metal oxide memristive devices and their characterization and application. I prepared this presentation with the assumption that not all of you will be familiar with memristors or in fact, applications in circuits. So I'll give a brief introduction as to why we care about memristors and what we plan to do with them. And I'll try to watch the time so I don't take more of your time than I should. So that's what I'll do first. I'll introduce the memristor and then talk about some why it's important, why we care about it. I'll talk about types of memristors, and then I'll talk about my own devices and how I characterize them, what I see, and how I aim to use them. So what is a memristor? It was first hypothesized by Professor Leon Chua back in the 1970s as part of a symmetricity argument. So he noticed that all circuit variables, so current, voltage, flux, and charge, were related to one another by a component. For example, the resistor relates current to voltage, but flux and charge weren't related to one another. So he started off with, what if there was a device that did that? And through his mathematical studies, he realized that it would be basically, the device would be like a resistor with memory. So its resistance would change according to its the characteristics of its excitation. And once the excitation signal was removed, if this device was non-volatile, it could retain its final state indefinitely until a new excitation was applied to it. So an ideal memristor would basically integrate the input. So on this slide, on the bottom is a very simple expression to give an idea of what a memristor would do. So if the input signal is a current, it would take the integral in time of current, and the voltage across it would be measured to reflect the changes in input in this way. So this, the first figure is dated on purpose because it's a figure from when the first prototype of the memristor was reported by HP Labs, basically over 30 years after its postulation. So they reported a titanium oxide device. The active layer is titanium oxide. Part of it is stoichiometric. The other part of it is doped. And the way this memory property comes about is in resistance change, as I just said. So conductance changes according to the state of the device. And how this is controlled is through an input signal. In this case, it's in the figure, it shows a voltage. So when a positive voltage is applied, oxygen vacancies spread out through the device. So the layer with oxygen vacancies becomes larger. So the device becomes more metallic, more conductive. And once that's removed and negative voltage is applied, the oxygen vacancies, positively charged vacancies, are drawn towards the top electrode where the voltage is applied, and the device becomes more insulating. So the effect of this is shown here. This plot is counterintuitively for a current input, so the x-axis is current, but the effect doesn't change. So what happens is when oxygen vacancies move, the device might start from the more conductive state, so this one. And after a certain point, due to the input, this device will switch to a more resistive state. So it will change resistance. And then the same will happen in the negative third quadrant. So this is different to a linear resistor. Obviously, a linear resistor would behave like the black dashed line here. It would, the resistance would not depend on frequency of the input. but with the memristor, we have a varying resistance, which translates to memory. These devices are passive, so for a positive input, we see a positive output, and vice versa for a negative. Okay, so that was an overview of a very brief overview of simple explanation of a memristor. Because I'm in electronics, I like to talk about transistors, and there's a lot of where memristors will be applied to is basically circuits involving transistors. The leading transistor technology used to be CMOS. It still is, but the change of the shape of transistors or topology of transistors changed over the years. Back in 1960s, Gordon Moore, who worked at Intel at the time, hypothesized that the number of transistors on a microchip, which is usually 1 centimeter squared, would double every 2 years. And this actually happened. He was right. Up until recently, when we hit a boundary, we're about to anyway, because the way in which number of transistors multiply isn't only through good design, but also through shrinking the devices. So they've become smaller and smaller over the years, and now the state of the art is 3 nanometers, or it's about to become 3 nanometers. And that's obviously very small. So we talk about, when we say size, it's pitch size, so the distance between the amount of space one transistor takes. So it starts from the beginning of one transistor till the beginning of the next one. So actually, the length of the gate, as shown here, is not 3 nanometers. It has to be smaller. So in order to keep up with this hypothesis, the shape of transistors changed, as I just said. So we start stacking these devices up. They're more three-dimensional devices, such as the FinFET shown here. So instead of a gate that's planar, this gate goes around the other terminals. I won't go into this too much, but I have some figures that I just checked recently. So the chip in iPhone 11, I think, is A13 apparently, and it has 8.5 billion transistors, and this was manufactured in 2019. And then in iPhone 14, I think, is A15 chips, and these have 15 billion. They also use different technologies. So A13 used 7 nanometer technology, slightly larger FinFETs, and A15 used 5 nanometer technology, so it's smaller. And the aim is they keep reporting that they'll manufacture a chip with 3 nanometer technology, but I'm assuming it's not very easy, obviously. So once that happens, that will be the next densest chip. But because we're at this boundary, it's not only trying to stack devices closer together, shrinking them. They're also looking at different shapes of transistors. We also have to look at alternative technologies or alternative ways of assembling circuits and alternative architectures or problem solving. So, everybody knows that neural networks is becoming a big topic. It's not only a software problem, it's also a hardware problem. So in order to be able to process a lot of data, we need to create more smarter ways of analyzing signals. So that includes neuromorphic design and also emerging devices, which I'll talk about now. So Intel is also aspiring to 1 trillion transistors by 2030. They have different technologies. So they have something that they call ribbon-FET. I think it's very similar to FinFETs with multiple gates. But so there's a lot of work in trying to keep up with Moore's law in still using CMOS. So as I said, different architectures require different ways of thinking, different ways of designing circuits. So this is just, again, I'll keep this very short, but different chips that use neuromorphic computing and their numbers of transistors that they use, what they call neurons, how many neurons they use, and their energy efficiency. So there are two on the right-hand side that are a little more different to the first three. Rolls and NeuroGrid use transistors in subthreshold mode, which is when the transistor works below a threshold voltage, which is what I'm interested in. And memristors are particularly suitable to be used in this regime because of the way their dynamics are mathematically. So these applications are less transistor heavy compared to True North or Loihi. And they can be very energy efficient because they don't consume as much voltage or current. So some guys working with memristor devices have identified certain roadblocks for traditional computing with traditional CMOS circuits. One of them is Moore's law, as I just talked about, and then there's a memory problem because the more we process, the more memory we need. There's also operational problems, a heat wall. And what they suggest, and what most people working in memristors look at, or most people working in CMOS even look at, is alternative ways to stay efficient. So like bio-inspired computing or better memory storage so that we can move on to the next stage of using this technology. So using memristors offers 3D integration because it can be stacked on top of CMOS technology. So we look at a more 3D design instead of a larger footprint on a planar level. And using these devices also create a better computational efficiency as well as power efficiency, on top of which different ways of solving problems are used, such as neuromorphic computing. So using memristors, several applications have been shown in the literature, and these guys have classified existing memristors into first order, second order, third order devices, which means if the state variable is a single, so conductance, for example, it's a first order device. So it has been shown that memristors can be used to do some image recognition, like identifying handwriting, or in the next one, it's still first order, the second. So these are also metal oxide devices, titanium oxide devices. So again, this is data patterning or image recognition. A second order device might have a state variable that's conductance again, but also temperature. And it can maybe solve more complicated problems like recognizing the speed of a video. And finally, they report a third order device using niobium oxide. And it has three state variables. So temperature, again, charge on the internal capacitor, which is impedance, so similar to memristors, and also the speed of Mott transition. And this has been used for a more complicated problem, viral genome problem. And so there's a lot of potential here. Slowly getting closer to my own devices. So memristors can be generally classified into three types. One of them is a cation device, or an electrochemical metallization memory called ECM, where the movement that's responsible for the conductance change from a low conductance to a higher conductance, or vice versa, is done by cations. So very typically, this can be due to an active top electrode like silver, and silver ions will move within the silver atoms will move within the device. The second type is valence change memory, or anion devices, where oxygen vacancies, for example, are responsible for the conductance change and memory. And finally, they call these devices dual ionic devices, where both types of species move within the device and create a conductance change. Okay, so these are my devices. And I've used titanium oxide as an active layer. So part of it is stoichiometric and part of it is doped. The top electrode is chrome capped with gold. This was a full wafer process using classical lithography with liftoff at every stage. Chromium was deposited using E-beam. Gold was deposited by thermal evaporation. The stoichiometric titanium dioxide was sputtered with RF sputtering, and the doped titanium oxide was created using a titanium target and while allowing some oxygen into the sputtering chamber. I've characterized these devices using IV measurements. And depending on where we look at the hysteresis loop, we can see distinct high resistive state and low resistive states. So 8 kilo ohms for around 0.4 volts. This is the input is voltage and the output is current. And the low resistive state, where it's more conductive, is 400 ohms. And closer to the origin, the gap between these two values change a little bit more. The ratio is higher. On the negative cycle, it's a less controlled measurement. So still, though, the high resistive state is very distinct, and the low resistive state varies a little bit between some values. We also look at some quantum effects in these devices. And in order to see these, we apply slow current ramps. And basically what this means is if a single filament forms, it's 1 G0, which is around 13 kilo ohms. And then if there are more, then so 2 filaments corresponds to 2 G0. And through these measurements, we can see quantum effects in these devices, and trying to harness these effects for circuit applications is a very exciting prospect. Or, you know, if you can't harness it, how do we use it is another good question. I also worked to fabricate similar devices with capping layer of platinum on top of chrome, but these devices have a thicker active layer and a thinner electrode, which translated to a much larger resistance, which I was aiming for, because I'm about to show you that I simulate circuits using the characteristics of these devices. So these are in the mega ohm region, the high resistive state and low resistive state values. They're fabricated in a similar fashion to the gold electrode devices, except platinum is deposited using E-beam. So what we do is we take these measurements and then we model these devices using curve fitting and or existing models. So we fit the data into existing MemRister models. And then we have to simulate circuits before even manufacturing them, because we don't know if it's going to work well with these devices. So the circuit that I show here is the half-center oscillator. It emulates the behavior of 2 neurons coupled together that fire reciprocally, which by that I mean, so the behavior is shown here. So say the yellow plot here is neuron I, and the blue plot here is neuron J. They're measured here. So one is here, the other one is here. And by adding memristors to this device, to this circuit, we can damp the oscillations and change the behavior of the half-center oscillator a little bit. So we did that, and this is a subthreshold circuit, so the currents are in the nanoamp region. So in order to be able to use the memristors, they needed to have very high resistances. So it was good that these memristors turned out to be so resistive. So we did some circuit simulations and saw that obviously adding some dynamic damping lessens the amplitude, and also the amplitude gets lower and lower as time goes on. Building on this, half-center oscillators can be coupled to one another. So 4 of these can be coupled to one another in a specific order to make up what are called central pattern generators. So central pattern generators are, again, biological circuits which control rhythms autonomously without the signal having to be sent to the brain. So walking is one such movement. Heartbeat, again, it's controlled by a central pattern generator. So coupling 4 of these together can emulate the movement of a 4-legged animal, like a horse, and coupling them in specific ways can emulate different ways of walking, different gait forms. So walking, trot, or gallop. So again, we looked at the effect of adding memristors to the system. So without the memristor, what it does, I know this is a little difficult to look at maybe, but what happens without the memristor is this circuit reaches an intelligible walk mode. So the right forelimb, left forelimb, and the hind limbs move in such a way that creates a walking motion. So the amplitude would translate to the stride length, and the rhythm of the oscillation, the frequency of oscillation, would translate to the pace of, if this was controlling a robot, for example, the pace of the robot. So without the memristor, the circuit reaches a walk mode that's intelligible, the limbs move in the right way, and then the amplitude stays stable, which can be good. But if we wanted to change the way something moved, we could add memristors to the system, and then the amplitude decreases because this is damping, but it's dynamic because the resistance keeps changing. So gradually decreases the amplitude, and also changes the frequency of oscillations. So towards the end of the timeline here, the period becomes larger. So it's a slower walk with a lower stride length. So it becomes much slower towards the end. So using memristors, we can, in fact, maybe change from one form of gate to another without having to reconfigure the circuit. So this is what I try to do with these titanium oxide devices. So to conclude, memristor devices are very suitable for beyond CMOS applications. So for the future, they're a good solution to keeping dimensions down, but also having a lot of processing power. The dynamics of memristors are very suitable for circuit applications, particularly subthreshold device circuits. And there's lots to work on, like quantum effects, behavior of very dense networks with CMOS devices, and different material combinations. Okay, so thank you for listening. And I'd like to thank the people I work with and our project. And I'm open to questions. Thank you.
Thank you very much, Itir, for this great and very interesting presentation. It is time for question.
Frederica, I have a question.
Yes.
Yes, thank you for your presentation. And I have a curiosity about your results, you are using titanium oxide. Is the titanium oxide the best oxide for this kind of memory stores, or there are more options? And the other thing is the thickness of this layer is critical. So if you can improve the properties, modifying the thickness of the device.
Yeah, so titanium oxide is not the only option. It was, I chose it because I wanted the devices to work, basically. It was a starting point. But there are many, I mean, I won't count, I won't try to count all the materials that can be used, but there are organic materials that are being used, even aerogels. So memory stones can be observed with a whole variety of materials. The thickness is critical. It does change the conductance and even switching. So if it's too thick, it might be difficult to create filaments or observe them. These are nanometers. So the gold capped one is 40 nanometers. The other one is 20 nanometers thick. Yeah. Thank you.
Okay, I have another question, if it's possible.
Sure.
So there is an example, or this is possible to fabricate flexible devices using memory stores. So because you are commenting the possibility to use organic materials, so this one application could be flexible memory store.
I actually have a work. They're macro, so they're not small. Using ionic liquid as a switching layer, but there are a lot of sophisticated work using again organic materials and other things with to create flexible memory stores. And they also look at the curvature and how that changes the behavior as well. So motion becomes a state variable. Yeah.
Thank you very much. Very interesting.
Thank you.
Other question? Yes.
Hello. Yeah.
Larry? Hi.
Hi. Yeah. So again, it was very interesting, and I guess you're right that most of us are not from this field, but we do more materials. So in this regard, and also referring to the previous question, what would be regarding the choosing the titanium oxide or other metal oxides, what would be the properties for a good material in this sense?
So I don't want to say anything that might upset anyone because I'm not a materials person. But what needs to happen is, so for example, the cation devices use silicon dioxide as an active layer, very typically. So what has to happen is that the ion has to be able to move or form some sort of filament within the switching layer. And
so
I think
higher ion diffusion.
Yeah, but maybe not too high because you want to be able to see, two extremes at least. And these devices have to be able, so the variables are voltage and current first and foremost, right? To be able to characterize these devices, to be able to measure anything. But I think it's very wide. So they can be controlled with light, heat, but some ionic movement has to happen. So.
Okay, thank you.
Thank you.
All right. May I have a quick question for you, Itir? I'm very I don't know this field, so I'm not sure it makes sense. But you showed this modeling of the horse walking, trotting, or galloping, right? Using the memory stiffs. Would it be possible to model a 3D motion with this system? Does it make sense?
What do you mean 3D motion?
Like some not a linear, like a 2D motion, like a walk, or because it's on speed, but would you be able to model something that is moving different directions
Oh,
instead of one, combining devices. It might not make sense, but I'm curious because I think the approach is very, very interesting. Oh, I lost. Can you hear me? Seems that we lost connection.
but it's a different.
Oops, I
sorry.
didn't. Yeah, sorry, I didn't hear you because you were frozen.
Did I
for 2
freeze?
seconds.
Yeah. Okay. So it would be. I'm sure it would be possible to control so whatever moves in a different direction, but as is the circuit, I can't control the different directions of it at the moment. And using memristors, again, the way we, so this circuit is only, so
Okay,
left, right, basically.
all right.
Yeah.
Okay. Thank you. Thank you very much.
Thank you.
So if there are no more questions, then we can thank our 2 speakers again for the nice and very interesting presentation. It's very diverse and always a great pleasure to listen to this Netpore communities activities. It was excellent. Thank you, Guido. Thank you, Iter, again.
Thank you.
And thank you, Louise. Thank you, everyone, for attending the webinar, and hope to see you again in a month and maybe before in person. Have a great day. Bye-bye.
Bye. Thank you.
Bye. Bye.
Bye bye.